So we have our next presentation titled Investigation of Materials and Structural Performance of 3D Printed Concrete. And our today's speaker for this presentation is Dr. Sriramya Nair. Professor Nair leads a research group at Cornell University focusing on supplementary and alternative cementitious materials to reduce the carbon footprint of the cement and concrete industry. She earned her PhD in civil engineering from the University of Texas at Austin, where she developed set-on-demand concrete using magnetariology. She held research positions at UT Austin and Cornell's High Energy Synchrotron Source. Nair received the ACI Walter P. Moore Junior Faculty Award and an Early Career Fellowship from the National Academy of Sciences. She is a voting member of various ACI technical committees like 123, ACI 236, ACI 238, ACI 564, and 565. So let's welcome our speaker today, and I'll and listen to her presentation.
Good morning, good afternoon, good evening, depending on where you're joining us from. Thank you so much today for joining. Like Aparna said, I'm going to be talking about investigation of material and structural performance of 3D printed concrete. So this is a brief outline of my talk. I'm going to talk about how robotics and automation can play a role in the construction industry. And then I'll specifically dive into 3D printing with concrete and the material properties that are required for 3D printing with concrete. I'll give you some examples of structural elements that we've printed and tested in our lab. And because with the theme of the day, I'll talk a little bit about how polymers can be utilized for 3D printed concrete. So before we dive in, of course, I don't do all the work myself. There's a lot of people that support and help the project that I'll be presenting today. And there are collaborators, students, alumni, and existing members that have contributed to this talk. So I would like to first thank them. So to get started with the talk, we have a very large landscape in terms of the variety of things that need to be done at the site before it's ready for construction. So for example, here, Built Robotics, this is from a few years ago, they were trying to see, because we have used a lot of heavy machinery on the site, if we could use them to automate them. And then also, let's say, for example, if you combine that with like an aerial survey drone and you have exact landscape of things that need to be done, then you can accomplish those tasks. However, automating such tasks is not trivial at this point of time, especially because the technology isn't there yet. There is a lot that needs to be developed. So that means that we shouldn't give up saying that this is a very complicated process. We should continue to invest in such technologies so that in the future, they become a reality. And the main, apart from the maturity of the technology, the other main problem is that a construction site is an ever-changing site. So it's not like, for example, car manufacturing where a robotic arm is used for a specific process over and over again. But in this case, our construction site is always changing. There's always new needs. And a construction site from one place is not the same as the construction needs that you have in a different site. So these are all existing challenges. But things that we can do today are like similar to the car manufacturing industry. If you have a repeated job that we need a robotic arm to do over and over again, then those are tasks where this robotic system really thrives. Automation, robotics, anything that you can think of, right, in this perspective. So here, this robotic arm is placing a brick and it has a specific path that it's going to travel, and then it plays a little bit of motor. So that means that the system is working really well. I don't know if you've built a wall before, but at Cornell University in some of our classes, all the undergrads and grad students build a wall and test how strong the wall is. And let me tell you, it's not easy at all. So we definitely need professionals to actually accomplish this job. But then we keep hearing about how there is a vacancy for skilled labor. So this is where the semi-automated mason can really help, because you can see how the lines are really straight, the wall is really vertical. So this is a very skilled example of how automation can be used. Similarly, this one is by Advanced Construction Robotics. So there's like an iron bot and a tie bot. So in the case of the iron bot, so when you have a lot of steel reinforcement that needs to be placed in a specific pattern, then this gantry style system that you have will pick up the will pick up the steel reinforcement and place it where you need it. And tie-bot is where, let's say you have like a warehouse that has a very good slab that cannot have any shrinkage or it cannot have any cracking, so has a lot of rebar in it. So then in such a situation, there's a lot of rebar that needs to be tied. So tie-bot is something that can be used for that scenario. There's a really nice YouTube video that you could watch where the iron bot and the tie bot are being used. And another thing that I'll come back to in a little bit, but you can see how this is like a gantry system. So if you were to, let's say, next need to pour concrete, so it's not even 3D printing with concrete, but let's say you have a pump and you just want to pump your concrete, this robotic arm can be used as well, where the head can be switched over to a new system that's just pouring your concrete, just as an example, because once you have the gantry system already in place, you can just use it for various tasks as long as they're repeated tasks and you tell the robotic arm specific directions where it needs to go. So there's like a lot that can be done in terms of robotics at a construction site. So I have another example over here. So this is an example from Cornell University by Professors Leslie Loke and Sasha Zivkovic. They also have their own company called Hannah, like an architectural design firm. And in this example, what they're trying to do is, instead of taking a wooden log and just cutting into 2x4s and generating a lot of waste, what you can see in this example over here is where they are maximizing the amount of wood that you can use for construction, and they actually used virtual reality to decide the shape, to first get a scan of the log and then decide where it needs to be cut and how it's going to get assembled. And so this is the first example of how they 3D printed a house and combined it with windows and the wooden. So the concrete is used where it's needed and the wooden pieces are used where it's needed. So it's mixing two different material systems and using them in the same construction. They used the similar technology for a Coachella installation this year in 2024. There's an article about it over here, but you can see how the bottom of these structures were 3D printed. So you can see the lines. So that's the telltale sign that something is 3D printed when you see this layer by layer printing process. So these were of course printed on one side and the layers where they built up, and then they tilted this after they printed it. And they also, the same concept works over here where the wooden pieces are being robotically constructed in such a way that you're stretching it and making it go further than you would with just a regular 2x4. So you can see how in this one, the robotic cuts here and cuts there. So, but then for transportation, this is actually quite easy because you can collapse everything and then transport it. And then at the side, you extend it and put the bolts in. There was a lot of structural design that went into this too, because these are tall structures, so they had to design them for wind. The same architects, Sasha and Leslie, they've also 3D printed a two-story house in Houston. They're also using a similar concept with the mix of using wood where it's needed and concrete where it's needed. So this one was printed with a Quikrete bagged mix and the Cobot Perry gantry style printing system. So you can see how the gantry is enveloping the size of the house, and they printed the two-story house, and the chimney was printed on site and then later tilted up. You can't see the chimney in this picture, but it shows up in other pictures. So you could use it for construction and printing on site. You can also use it for precast, where you print a specific member and then you bring it to the site and you erect it. So both cast in place or precast or cast on site, and then that's erected for construction. So when you think of houses, of course, you think of Icon as well. Icon has 3D printed houses. Right now, they're printing a 100-story house in Texas. There is another like segment on that was on CBS in 16 minutes. There's a YouTube video about it as well. But they have taken 3D printing to the next level because they're not just printing the house, but they're finishing them. So it's the entire package, right? Where the company does everything from start to finish. So these are some examples of how robotics could play a role. But the question here is, why do we want to 3D print with concrete? Like, what's the driving force? So one of the driving forces is always cost, right? So in terms of, if you look at cost, labor cost is about 34%, and then formwork cost is 20%, right? So concrete takes the shape of the formwork that we place, and then so any shape that's our formwork, then that's how the concrete can be. But if you want to have like complex geometries or just change the shape of what you want to do, then the formwork cost and the labor for the formwork cost really increases. And there is, we all hear about it, but there's definitely like a labor shortage right now, and that labor shortage is only increasing. And especially by 2060, it is expected that our materials needs for like civil infrastructure, right? Like that's in terms of sand, gravel that's used for construction, that goes into concrete as well. That is going to almost double. So, and then that means our infrastructure is aging. There are a lot of people that are moving to cities. So we're going to continue building, and construction is going to be a booming sector, and it's going to need a lot of labor. So, but where are these skilled labor forces going to come from? And are there technologies that we can use to leverage this shortage, but also have create jobs in a different sector, which is basically in these automation. So, for example, here in this, what I'm showing you is, I'll show you another picture of this later on, but these are steps that we printed in our lab, and you can see how it's like a complex geometry, but then there is a lot of space in the middle. That means that we are minimizing the overall amount of material that's needed for construction, and it's also a complex geometry, and you don't need a formwork for it. So if you have an optimized shape like this, like I said, there's like hollow spaces in the inside, you're using less material. Less material means lower emissions. So when we talk about concrete and we talk about emissions, we always talk about, okay, cement is the one that's emitting the most CO2. What can we do to minimize cement, and what can we do to replace cement with like lower embodied factor materials, like we always use supplementary cementitious materials, for example. But another way to lower emissions is to just use less material. And also with 3D printing, if you don't have any formwork, that means that you're not generating waste. Especially when you have complex geometries, the formwork will typically be used only once. And then even if you use it a few times, it always ends up in landfill. And finally, with automated construction, you need fewer people on site, so that way you can get the job done much faster, needing less people. And 3D printing is projected to be a growing market. By 2030. It's expected to reach about like $1 billion. So this is like from a report. And so there is potential for 3D printing, and which we can already see, because if you think of it, this like 5 years ago, there were very few examples of 3D printed structures, but right now there's so many. I only showed you like a small sliver of examples, but there's just so many more that you can go and find online. So there is definitely a lot of interest. We're going to see a continued growth in terms of the potential market for 3D printing in construction. So what is 3D printing and how does it work, right? There are two main inputs that you need. The first one is you need to have a design. So you need to have an idea in mind about how are you going to design it. So it's not just that I want to print a column, but it's about what is the shape the column is taking, and also what is the tool path that the robotic arm is going to take such that you can print that shape. and then you need to slice it so that layer by layer printing can happen, and then you extract that information. So then you send that information to the robotic arm. The second piece of input that you need is the material system. So you know where you need to go, but you also need to know what you need to deposit. So for that, you need to have a mixture. In this case, of course, we're going to be talking about 3D printing. I mean, you could also be printing with plastic, let's say if it was like a smaller system, but here it's concrete. So you need to be able to mix it, pump it, and deposit it. So in this case, the deposition is by extrusion. So like I said, let's say this is the column that we have in mind. This is like a two-layer system where inside is like a circle and outside has a complex geometry. So then you need to figure out how you want to slice it, and then you extract points because the robotic arm needs to know where it needs to go next. And this is the information that you feed into the software. So in the mixing process, this is an example of what we do in our lab. So we have a Waterman mixer where it's usually used for mortar, and the pump that we have here from the X-ray system, the maximum particle size is 2 millimeters. So because there's no coarse aggregates in it, this mixer works really well for us. So in this system that we have, the pump is missing over here, but you place your mortar in there. There's like a vein that constantly keeps the material shearing, and then you pump the material from here, and then it goes through these black hoses and gets delivered to the nozzle, and the nozzle will go and deposit the layer exactly how we had planned it, like, from one spot to the next spot. So in our lab, we have this robotic system, but you could either use like the 6-axis robotic system, or like here, it's sliding over here. So that means that gives you like a 7th axis because the whole robotic arm can slide in itself. So you could either have like a 6-axis or 7-axis robotic system, or you could also have a gantry system, similar to the one that I showed you where they printed the house in Houston and also the Coachella installations. That was using this Cobord Perry system where you have a gantry. So when you have a gantry, it needs to envelop the whole element that you're printing. But when you have a robotic arm, you can strategically place it in certain locations, or you can move it to a different location, or have multiple robotic arms that work at the same time and print different parts of the house. So it all depends on the needs of that site. So you have two different types. So this is just two examples that are most commonly used, but for either of these systems, there are two different ways in which you can deliver that material system. So there's a one-stage system and there's a two-stage system. In the one-stage system, what you have is, it's almost like the bag mixes you get for UHPC, ultra high performance concrete, where you have all the additives, everything that goes in the bag. So you have like your mixtures, you could have like fibers, polymeric fibers, and then you can just add water. So you have a pumping system where the dry material comes in and the water gets injected, and then you mix the two. And right after you mix them, these materials are highly thixotropic. I'll go into this a little bit. Basically, what this means is, as you're shearing the system, it'll like remain pumpable, and but then once you stop pumping, it can hold its shape and have good buildability. So these typically have very short open times because right after you mix the water with the material system, you just want to deposit right away. So that's could be like 10 minutes, 20 minutes. It just depends on the material system. There are obviously mixture designs that are coming up where that can give you like longer open times, but typically right now they all have very short open times. The other thing with the one-stage system is that obviously you need to have these dry mix that is like mixed really well within the bag. Like you don't want any segregation within the dry mix. So that means typically these have to be designed really well. But in our lab, we don't have the capability of doing the dry mix on the large scale. So that's why we prefer the two-stage system. So like I showed you with the Mortimer mixer, we can mix a very flowable mixture. And then it just has you can think of it similar to UHPC. It's very flowable, but doesn't have the steel fibers in them because our pump cannot pump steel fibers and like really stiff fibers, and it also cannot pump, like I said, larger than 2 millimeter particle size. So in our case, because we have a very flowable mixture, we inject an accelerator at the nozzle. So this is what makes it two stages. The first stage is mixing and pumping it, and the second stage is the addition of the accelerator, such that once the accelerator starts working, then it's like a chemical additive, then you can achieve buildability. And you can typically have longer open times, but this is from the flowable mixture perspective. Once you add the accelerator, though, it's very close to the nozzle, and you want to be able to print right away. So the open time is for the flowable part till it gets to the accelerator. So this is how, this is from this, I have citations, so this is from this paper. We can see how this is the log of the yield stress. So this is like if you were to do like a rheology test and measure the yield stress of the material. So during pumping, you want a very low yield stress. But during deposition, you want this transition to be really quick. So you want this is what thixotropy is, right? So you want this transition to be really, really quick. And you can design materials like that. So you can design materials that are highly thixotropic. So this is like the area under the curve gives you an indication for how thixotropic a material is. The larger the area, the more thixotropic the material is. So to get this really fast structural buildup, there are systems that we could use. Like for example, VMA is a viscosity modifying admixture. We already use them in concrete, specifically, let's say, self-consolidating concrete, where you have flocculation of particles, which really helps with building up that structure. And you could also use clays, and these are typically like flowable during extrusion. But then once they're at rest, they have that house of cards effect where they have like a specific structure to them. And then you can get like that, during that deposition, this increase in yield stress that we are looking for. So you could also use polymeric fibers that could also create this 3D structure at rest. But then in this two-stage pumping systems, because we are pumping the material, you design it such that it's typically not thixotropic, and then the yield stress is like, maintains its yield stress over a period of time, and it's not changing so that, you don't have increase in pumping pressures. So it is really difficult to measure the thixotropy offered from like once you add the accelerator, because it stiffens up really fast and you won't be able to measure it using a rheometer. But for that transition to happen, shotcrete accelerators are very commonly used. So you use the same accelerator that you would use in shotcrete application, but then you inject it at the nozzle. So since you cannot use a rheometer to measure that transition, what you could do is you measure green strength of concrete. So what you do is you take the material after you've injected the accelerator. So you could use this both for one-stage or two-stage systems, and then you can make a cylinder. And then there's obviously no ASTM standard for this, so people have developed this technique. But you can have, let's say, a cylinder, and then you keep the cylinder and you remove the sleeve on the outside, and then you measure compressive strength at different points of time. So you can do this before 30 minutes too. It all depends on how fast is it able to hold its shape right after you mix your accelerator. So in this case, they did these tests like 30 minutes, 120 minutes, and you can see gradually like this is at 30 minutes, the pink line in the bottom here, and the blue line is at 150 minutes. So obviously the amount of vertical load these samples are able to take on is increasing with time. And this also gives you an indication for when you print your material system, how much load it will be able to carry, which is basically the other layers that are being placed on top of it, or the robotic arm pushing the material down on top of the other material. So they're like forces that are being acted on the bottom layer that has been deposited. So green strength is really important and gives you a lot of information about how your printed structure is going to behave. So another material design consideration that you have to keep in mind for 3D printing is plastic shrinkage. Like I said, most pumps right now are limited to 2 millimeter maximum aggregate size, and they also need a high paste content to ensure that the material is pumpable. So in that scenario, you need to minimize the amount of cementitious content that you have. You can still have a large powder content similar to what you have with UHPC, but you need to reduce your reactive content so you can minimize your shrinkage. You can also use the flexible plastic fibers or glass fibers. As long as they're flexible and thin and the pump won't get damaged, then you should be fine and you can use them for plastic shrinkage. So when you're thinking about your mixture, end of the day, you need to think about, can you pump that material? Will it stay uniform? Will there be segregation during pumpability? Which we already know a lot about because we're really good at pumping the concrete. But in this case, it's not just about pumping the concrete, but the concrete that comes out of the nozzle needs to be extrudable. It needs to be able to hold its own shape and needs to be buildable. That means that you can do that layer by layer building so that you can achieve the height that you need. And to achieve that, you also need to have really good green strength, so that early strength as it's aging with minimum plastic shrinkage, so you're doing the least amount of damage to your designs. So keeping all these in mind, we have a mixture that we developed in-house such so that we know our water to cement ratio and what's going into our mixtures. So we have a paste volume. So this is not cement paste, but it's just the powder paste content, which is 52%, of which we're using 30% supplementary cementitious materials right now. And our nominal aggregate size is 2 millimeters. We use a high range water reducer such that this material system is flowable, and we get about, so we use the flow mortar table test, that small slump cone, and then we pour the material and lift it up. So almost like an SEC, it just flows. And then you measure the diameter of that slump flow, which is about 17 centimeters in this case. And then we inject an accelerator at the nozzle. So inside this box over here, so we have a injector that gets the chemical gets injected, and then it gets sheared in and then just comes out of this metal nozzle right here, and the material gets deposited. So our material has a compressive strength about 10,800 psi, so it's like really strong, and we also have a very good flexural strength about 800 psi. And we also did a bonding test to make sure that the layers have a very good bond strength, and which is why we were able to use these as steps. So like I said, we printed this geometry and then we tilted it to the side, and we are using these as steps. So like this is an example of how a typical reinforced concrete stairs could look like. Of course, the span here is small, but what I want to show you is how this was designed such that because concrete is really good in compression, we designed arches such that the forces are transferred onto the arch in a compressive manner. And because the layer-to-layer bonding is so good, we're able to use them as stairs. We also put like a huge point load to make sure that this was strong enough to take like 1,000 pounds in like a small square foot of area. So, like I said, because concrete is good under compression, we've also printed these arches. This is from a course that I teach. It's called Sustainability and Automation, the Future of Construction Industry. So this is an example from a couple of years ago in a project where the students did their own mixture. So this mixture actually has a lower carbon footprint than the other mix that I showed you. So they designed this mixture, first the low embodied carbon factor mixture, and secondly, they also designed this arch such that it is using less overall amount of material, but it is printable. So this shape that is it's taking, there's no sharp corners, so it's able to print really well. And then we tested it under compression. So along that same theme, because right now, obviously you can all see that there's like no reinforcement in any of the things we are printing right now. We are trying to maximize and see how concrete can be used in compression, right? So we are maximizing the material usage in compression. So in general, when you look up what happens in nature, gyroids show up a few times, and they're supposed to be good in compression on all sides, and they're supposed to be very efficient in distributing these compressive loads. But the challenge is that you have these cantilevers. So for example, in this arch, previous example, is the same shape that's printed over and over again. Similarly to these steps, it's the same shape that's printed over and over again. But then when you look at this gyroid, the shape is changing. So if you were to 3D print this one, each of these, as you're going along that vertical height, each of them have like a different layer system. right? So then the question is, how can we effectively print those steep cantilevers? And can we really achieve a overall lower carbon footprint by optimizing the use of these gyroids inside a structural element? So to understand what we can actually print in terms of these gyroids, so we design these tests. So if you were to print a layer on top of each other, so that would be like a 90-degree. But here, let's say we want to print layers that are at a 63-degree angle, or a 56-degree angle, or a 45-degree angle. So 45-degree would be the steepest cantilever, and it would use the least amount of material. So for example, in this case, you can see how the hollow space over here is really large for the case of a 45-degree angle, but in this case, you have more volume because you need a larger sine curve to fill that space. So gyroids are basically sine curves in 3 different directions, and you can stretch them in different ways to achieve the shape that you need. So we printed them, these like 500 meter cube cubes of these different geometries. And then for the 45-degree case, we were able to print it. We did not really have that much issues. But this is one side of the cube, and this is the other side of the cube. That's on the back side over here. But you can see how in this specific case over here, in this, I don't know if you can see my arrow, but here, what is happening is you're placing a layer, but then immediately you're following the path right back. So it hasn't had an opportunity to stiffen yet, and then that's how it's falling down. And so the tool path that you use plays a huge role. But it also happened that this 45-degree geometry, like within like a couple of hours, had some shrinkage. It could be because the cantilever was too much for it to hold, but it could also be like some issues that happened with this specific print. But with the 56-degree and the 63 degrees, we were able to print them without any challenges. And then we also tested them because that's what we like doing. We print something and then we break it. And then we tested 3 of these cubes in this load frame. And this is how our load versus displacement curves looks like. So all this data that I'm showing right now is from this paper. So you can go look it up if you want to read more details. But the main thing that I want to show you here is that all 3 of them had like similar loads that I could take. But then the one thing that you can see is this slope, this angle right here is similar. So these are 3 replicates of the same system. But there's definitely challenges in terms of how are you loading it. Each structural element has a lot of variability. This is something people have seen with cube testing too. So if you were to print layers and then take small cubes and cut them, there is a lot of more coefficient of variance than you would see with like cast samples. So this is something that's expected, but also in this case, this could mean that the crack patterns in each of the 3 cubes that were tested could be just slightly different enough. And also like the top could be like not uniform in all the cases. So there's some issues with how you would test and print them. So these are all things that we're working on in my lab. So we've also extended this work and we've printed gyroids as a wall. This is about like a 6-foot tall wall that we printed and tested under compression. We have played around with toolpath designs. We played around with the geometry shapes. We've learned a lot and we are continuing to work in this space to understand how gyroids can play a role in structural elements. So here it's walls, but there are like other elements in which gyroids and optimizing your infill geometry could play a role. So, and like I said, there's just a lot of information that's available in this space of how do you design your material and what kind of shapes do you want to print and test. And it's just endless information that's available about these systems. But in the remaining 10 minutes or so that we have, the final thing that I want to talk about is how can we use polymers for 3D printing, right? So we did a small study when Monique was a postdoc over here in my group, where what we did was we replaced the cementitious part with SBR, which is the styributadiene rubber latex, and we replaced them in different proportions. So that's like S5 would be like, 5% SBR in the mixture. So we design these different mixtures, and then you can see that the high range water reducer components are changing. This is because you want to achieve a certain flowability. So when you achieve a certain flowability, you can see how as you're increasing the amount of SPR inside your mixture, of course, our compressive strength is going down. But as expected, the interesting thing is that your flexural strength doesn't increase at the same rate. So let's say here our control is like 6 megapascals for flexural strength and 90 megapascals for compressive strength. But then here, even though your compressive strength goes down to 40 megapascals. But here, again, this is the whole point though. Like 40 megapascal is not a weak concrete. It's still good enough. We could just be over designing our concrete. For example, for the steps that we've printed in our lab, for the short span that we have, do we really need 10,000 psi concrete? That's a very good question. So this compressive strength could be good enough. It all depends on the application that you're using it for. And also, how are you maximizing this compressive strength and how you're using it? For example, the gyroids, because they're good in compression, and it all depends on how the load is getting transferred. If you also need some higher improved, flexural strength, then you could use these flexible material systems like SPR. So we also talked about how compressive strength is not the only thing that's important for to be able to 3D print. We also need to know about the yield stress evolution, and thixotropy. So this is like the experimental setup. So we have this Brookfield viscometer, and then we do this shear ramp, and then you see what this peak maximum shear stress is, yield stress is, and then the area under the curve is the thixotropy. The main thing that I want to mention with this test is that your material needs to be really flowable for you to be able to do this test. If your material is really stiff, like you're able to measure like a good green strength, then that means that your vein inside will not be able to move, or even if it rotates, it just makes a hollow space. So you want to make sure that you're observing your material system as you're doing these tests. So you need to have a flowable mix to be able to do these tests. So this is how this yield stress is changing as you are increasing your SPR content. So it's becoming like you need less force to be able to move the material system. And it's also becoming less thixotropic as you are adding more SPR content into this material system. So because the large scale printing system that I've been showing you with X3, we usually, when we print, we are mixing about batches of like 50 to 75 liters, and we print about 200, 300 liters. But then when you're just doing like a material development, in this case, we're trying to see, can we print with SPR, and to what extent can our material properties improve? This is more like a experimental studies, so we don't want to be experimenting with like 200 liters of material system. So for that purpose, what we did was we built our own gantry printer in the lab, so that way that you only need about 4 liters of material system, and you can print and measure buildability, extrudability, all these things that are important for 3D printing. So this has about a 2 feet by 2 feet by 10 feet printing area. Kitty Pong, he's undergrad in my group, and he's the one that developed this printing system. So as you can see over here, we are able to do the layer by layer extrusion, and we are able to make the printer go where we need to go. So it definitely works, and we're able to do these buildability tests. So we printed both single walls and double walls. So this is like a single wall system. So the C is the control, and S15 is with the 15% of SPR inside the mix. And you can see both of them collapsed about like at 6 layers. And then, but when you print like a double wall, because it's more structurally stable, you're able to build more layers. So again, buildability depends on what are you trying to achieve, because there are no standards for buildability, extrudability, green strength right now. You'll have to decide what's a good test for you, and it all depends on, end of the day, what do you want to do with these material systems. In our case, what we were doing is we were taking these samples and then we were cutting them, and then we were doing flexural strength to measure the bond strength between, which I'll show you in the next slide. So this is a sufficient print to be able to do. And you can also see that there's like a lot of variables that go in here as well. It's like this layer height and where your extrusion nozzle is as you are depositing the material. That will also affect your bond strength between the material systems. And this one specifically has very good buildability because the shape of your layer is not like becoming like a pancake, like it's not getting like smushed as you're placing more layers. It's able to hold on to its shape. You also don't have excessive tearing as your material is being placed. So all this to say, there is a lot that goes into developing a material that's actually printable. So this is actually takes like a lot of hours to get to where this point is. So what we did was, like I said, we printed a bunch of layers and then we cut them such that we have like a specific coupon size, and then we tested them to measure the bond strength. So the control failed right here at the bond, and then for the SPR 15 mix, where you have 15% of SPR, you could see it didn't fail at the bond, but it failed in the system, and it actually had a higher shear strength than the control over here. You can see there's some aggregates in the mixture as well. So you can see that the addition of SPR resulted in a decrease in compressive strength while it increased flexural strength, and also the SPR resulted in a decrease in both static yield stress and thixotropy. So it could mean that you're pumping your material system might be a little easier with the SPR, and we're also shown that you could achieve printable mixtures with using SPR inside your mixtures. We did not see any interlayer bonding, but like I said, there's a lot that goes into how your printer is placing the material, how the next layer is being placed. The bond between those two layers is dependent also on the layer width and the composition of your material system. So you have to do those tests before you actually use these in real life. And the main thing is you want to make sure that you want to improve performance while maintaining printability, especially because your thixotropy is going down. And this one is almost like the one-stage system. It's not a two-stage system, and we did not have accelerators in this one. So there's a little more thought that needs to be placed into deciding how do you want to achieve the printability. So there's a lot more that needs to be done in this space. So finally, yeah, again, I would like to thank all the people that were involved. This picture is actually like a year old at this point of time, or more than a year old, and we've continued printing. So thank you so much for listening, and please let me know if you have questions.
Thank you, Dr. Ramya, for the excellent presentation. We really liked how you started your presentation with the overall view, and then you came to material properties. So that was really interesting. We have one question, and for the audience, if you have more questions for Dr. Ramya, please write it in the question box. It should be on the uppermost panel if you are not able to find it. Yeah. So our first question is. So when you talked about the 3D printing in 3D printing houses, which is currently going on, what do you think about the carbon footprint, and can it be reduced to any degree?
Yes. A lot of the houses that are being printed, they're being printed with custom materials, custom developed materials. So we actually don't know what the exact carbon footprint of the material system is. For example, if you're using less cement, high paste content, but if you're replacing your cement with other low carbon materials, so the carbon footprint could be low. So that's one point. We need to keep that in mind. I actually don't know what most of the mixture designs are because they're proprietary, but in our lab specifically, we're trying to keep it to a minimum. It also helps with plastic shrinkage, like I said. And the second one is, it's again about the shape optimization. So if you're able to optimize your shape such that you are using only amount of cement that you need for achieving the strengths that, because if you're only building like a two-story house, for example, you don't need it to be really, really strong concrete. So you want to maximize that performance too and not overuse your material systems. So from that perspective, there is a lot that can be done. And yeah, because like
Yeah,
I said, we don't know exactly what's in the materials. It's just a little bit of a challenge. Yeah,
yeah, we are still maybe at the beginning to optimize it.
exactly. Exactly.
Um,
There's a lot that can be done. But also because I think the market right now is not that large, that means that companies have to do a lot to develop these materials, bag them, and print them. So I think as more and more applications come in and more people start using it, they have an incentive to optimize these mixtures too.
mhm. Thank you. Uh, I can see one of the hand is raised. Islam, can you please write your question in the question box? Thank you. And our next question is, what do you think the role of polymers in 3D printing and how sustainable it would be?
Yeah. So from the use of plastic fibers to reduce plastic shrinkage, it's definitely useful. We should definitely consider that, especially because you can print with them. That's not a problem. Like you only need a very small percentage of them for improving the flexural performance, but from a plastic shrinkage perspective. But from an SBR perspective, again, like I said, it depends on how much you want to add. If you're only adding 10% of polymers, it's not a lot. But then if you're gaining that in terms of flexural strength or improved bond performance, then that is something that could you have to take into consideration. I think we shouldn't look at embodied factor as just per meter cube, how much is it, but it's also about like the overall structure. It's about like, if I were using like conventional materials versus 3D printing, what is that difference?
Great. Yeah. Thank you. Our next question is, do you think the durability of these structures, is there any study on the durability aspect?
There are a lot of ongoing research studies on improving durability. Obviously, that's where I keep talking about plastic shrinkage because that's really important. We also have these layers, and some researchers have found that the porosity at the layers is a little higher, which means that you could have more ingress of fluids, which could be possible. But no, there are a lot of studies that are underway. Again, Sean Monkman at Icon right now, he was talking recently about how there are like 600 papers. No, there were like 200 or 300 papers with 600 mixture designs on 3D printing. So there's like, again, it depends on what type of material system are you using and how durable they are. And again, you're introducing 3D printing. There are different ways of printing, the layer height, the layer width, and how you're extruding. There's just so many factors that affect durability. So that means you have to be testing these for different material systems, different types of printing systems, and they're all ongoing. They're all happening right now. And there's also a consortium right now at NIST. It's called the ACE, Additive Construction by Extrusion, where they're bringing people together at the consortium so that instead of different people doing different studies, we're all trying to combine our efforts so that we can address these problems.
Okay, great. Yeah, I think it's still a lot to achieve.
Absolutely. This is, like you said, this is just the beginning, and there's just so many questions that need to be answered, standards that need to be developed, both through ASTM and ACI. And so all these efforts are ongoing right now.
Mhm. Yeah, we have a question. I think it's more like a comment. For houses, I do believe that carbon content is higher since most of the houses using the printing as formwork and post-printing grouting.
Yeah, because some of them are also putting rebar and grouting, so you could use it as like a masonry. But these are all just like pushing the technology forward. It's like showing what's feasible. And now that we know this is feasible, then we can just make it better, right? So this is how
Yeah.
I started my first slide too, right? Like if you want to think of the whole construction side, it's not achievable right now. But if we keep thinking of that perspective, like, this is our goal, then we get started, show something, proof of
Hmm.
concept, and then we make it better. I agree with you that right now it might not be sustainable, but there's so much we could be doing.
Yeah. Like it needs more optimization, but it needs, at the same time, it needs more proving the concept. Yeah. Mhm.
Exactly. Yeah.
So yeah, we can give like maybe couple of minutes for audience to write the question if they have any. Um, yeah, I don't see any question coming, so maybe thank you so much, Sriramya, for this excellent presentation, and I definitely believe that all the audience have benefited from this presentation. Thank you so much.
Thank you so much. Yeah. Bye.